So first, I'd like to thank the organizing committee for inviting me today. I'm going to be talking about some of my work focused on how I can extract insight from hyperspectral imaging of materials using deep recurrent neural networks. So most of my work focuses on a class of materials called ferroelectrics. And because this is a pretty mixed audience, I'll give a very brief primer on what a ferroelectric is. So ferroelectric, most of the ferroelectrics that I work in exist in this perovskite structure, and above a temperature known as the Curie temperature, they exist in a cubic centrosymmetric state. When you cool below that Curie temperature, the B-site cation, the sending cation, distorts within the unit cell, giving rise to a spontaneous polarization. So you see the emergence of this polarization, and you also get anomalies in the dielectric response and the various properties of the material. Because this is a ferroelectric material, they exhibit classical ferroelectric hysteresis, where you can switch the material between different states. So if you apply an electric field, the material can align into one polarization direction, depending on the direction of the field, and then they remain stable in that state at zero bias. If you apply the opposite electric field, they'll switch to the opposite state, and again, they remain stable under zero bias. So the reason why I think this class of materials is so interesting is because they have a range of different really interesting and useful coupled functionalities. So for instance, if you were to apply an electric field to these materials, you can exhibit a strain, like the piezoelectric effect in these materials. If you apply an electric field, you can switch the polarization. If you apply a strain, you can change the polarization state. If you change the temperature, for instance, you can change the polarization, and that can be used to sense changes in temperature, or also could be used for energy harvesting in these materials. There's a really interesting kind of coupled effect where if you apply an electric field, you can use these materials as an entropy pump. So you apply an electric field, the system orders, and then as it disorders, it absorbs heat from the environment. So that can be used as a really efficient way to cool materials. So there's some recent work looking at this electrocaloric effect where it's used for harvesting low quality waste heat energy, so under 200 degrees Celsius. So it has a lot of implications for harvesting waste heat energy from and cooling electronic processors. So you can think about these materials are useful for piezoelectrics that could be sensing actuation, so moving objects around very precisely. They can be used for pyroelectrics, so either absorbing waste heat energy from processing units or doing thermal imaging. And they can be used for electrocaloric effects, so trying to cool things in a very efficient way using these materials. Another really interesting potential application of these materials is these materials are intrinsically radiation hardened. So all the time we're being bombarded by cosmic background radiation, and our memory is very susceptible to that, or can be susceptible to that, particularly as the memory size shrinks. We're more and more likely to get bit flips. So where a bit, which would be a 1, flips to a 0. Now generally that's not that important, but there are instances, for instance, the Toyota accelerator problem was eventually correlated back to a bit flip that was occurring, that was causing the accelerator to remain open. So these can have really serious implications, and this problem of cosmic background radiation is particularly important if you tried to use any sort of memory material in space where there's a lot more cosmic background radiation. So these materials provide an opportunity to create memories that are intrinsically radiation hardened, but also can have increased performance, including existing in multiple states beyond just binary. So in this class of materials, you can get these materials to exist in a lot of different crystal structures, each with slightly different properties. And you can think about how you can use different tools to engineer the crystal structure, and that affects the electric conductivity, the dielectric constant. So these are used in tunable dielectric materials for your 5G wireless devices. You can think about how you can tune the elastic modulus, piezoresponse, all by changing the crystal structure. Also, by having boundaries between different types of crystal structures or different domain variants, you can create really useful and functional properties like locally conductive domain walls, and create all sorts of different complex switching behavior that can be used to store information, can change the susceptibility, how they respond to any external stimuli that can be used in functional ways. So a lot of my work focuses on how I can think about designing domain structures. And when I think about designing domain structures, I have to think about how I can use the tools that I have and the energies that I have. So in these materials, you have a Landau energy, which is what drives that polar distortion, so that distortion in the B-site cation. But if you have a thin film of this material, it creates a strong depolarization field. You can kind of remember that from your early physics class in high school. And that causes the material to break down into antipolar domains to compensate for that depolarization field. I grow materials in thin film, so I grow it on a substrate, and that substrate has a crystal structure and a lattice parameter. And if I were to take a unit cell, so this is a tetragonal unit cell, and if this A value, this in-plane value, were to be slightly different than the substrate I grow it on, I can use that to strain the material. So I can pull on the material at the atomic scale and drive it to arrange in different interesting structures that provide different functionality. So this is called strain engineering. It's very powerful. Also, when I think about designing these materials, I have to think about what happens at the boundary between two different variants. What is the energy of the divergence and the polarization at those boundaries? So I'm an experimentalist, so I make materials. So I use this technique called pulse laser deposition. It's actually very simple. You just take a laser, and this is a vacuum chamber. You fire it at a target. This creates a plasma plume, which is then forward accelerated onto a substrate, which is mounted on a heater. And this allows you to deposit a really wide variety of materials. It's not the cleanest method of synthesis, but as long as you can put it into the chamber, you can grow it to some capacity, as long as it will absorb the laser wavelength. You can also, by tuning the various parameters, you can use it to control the stoichiometry and control the defects in the material. So one area that my group is working on developing is actually doing in situ characterization of the plume dynamics using high-speed imaging, because the shape of this plume has all of the information about the stoichiometry and the energy of the atoms as they're coming into the surface and arranging on the surface to actually grow a film and make a material. So I was looking at this very classical system. So this is a lead titanate system or PZT system. And I was looking at the phase diagram, and I noticed something that bothered me as a classically trained material scientist. So as a material scientist, we know that at boundaries between two single phase regions, there's this rule called the Gibbs phase rule, and there should exist a two-phase region. So here I have this domain structure, which is known as CA. So C means out of plane poled, A means in plane poled domain structure. And then there's this A1, A2 domain region, which is two variants of in-plane poled A domains. But if I look at this phase diagram that's calculated from kind of computational results, I don't see any two-phase region at that boundary. But if I look at the available substrates that I have, so these are different materials, I can find a substrate that has an appropriate strain to be right at that boundary. And if I grow that material, I get this hierarchical domain structure that is actually the two-phase region between these two different domain variants. So that's good. It confirms what I was thinking. If we go in and we do all the relevant characterization that we need to do to confirm that what we have is what we think we have, everything makes sense. So this is piezo response force microscopy images. So I'll talk more about what those are later, but this is an image of the height. This is the vertical amplitude, so that's the piezo response in the out-of-plane direction. And this is the in-plane response. So we can see we have this CA-like domain structure. This is the A1, A2 domain structure. If we take it to the synchrotron and we do X-ray diffraction, we can see that we have this exact structure that we would expect. All the lattice parameters make sense. The tilts make sense. They match with the AFM images. Everything is good. But the question then becomes is how does switching happen in this material? What are the dynamics of this really complicated system with hierarchical structures that are all interacting with one another? So for this work, I turned to some collaborators at Oak Ridge National Lab, and they developed this technique called band excitation piezo response force microscopy. So this is a scanning probe-based technique. So you have this little probe, and it's physically touching your surface. And you can use that probe to measure different things about the surface. And this probe is nanometers in size, so that at the tip, it's between 20 and 30 nanometers in size. And in this case, we have a conductive tip. So we can actually apply an electric field and drive transformations in that material. So what we do is we go to every single pixel position on this map, and we apply a bipolar triangular waveform. And what that's doing is that's switching the material from the down to up hold state. And in these steps, when we have these off-bias steps, we apply this band excitation waveform. So this is a waveform that has a spectral density across a band of frequencies near the cantilever resonance. So when we do that, we can measure out the full cantilever resonance. So this is the resonance behavior of the cantilever as we drive it with the electric field. And we can extract these ferroelectric hysteresis loops. So at every single point, at every single step, we have these resonance responses. So it's a 5-dimensional data set, 6-dimensional. And then we can go and we can fit this resonance character, and we can extract things like the amplitude, the quality factor, which tells you about how much energy the material is absorbing when we apply this band excitation waveform. We can extract the resonance frequency, which provides insight about the elastic modulus of the material. And we can look at the phase, which tells you about the sign of the response. So we have these image series or spectral series, hyperspectral images, where we have the amplitude, phase, loss, and resonance frequency at every single pixel position. So this is a pretty big interacting data set where there's a lot of information inside. We don't know how to extract that information. If we were to even just look at example hysteresis loops, so this is just one of the channels, and look at the shapes, we can see a lot of fine structure in these individual response curves that just can't be fit with an empirical function well. So the question is, how can we go and extract more information from this data? So when I was thinking about how to apply machine learning, I was thinking I want something that's going to be generalizable. So if I explore my data set manually, I can see I have some hysteresis loops that look like this, some that have multiple steps, and all these are important for me to understand the physics. But I need to be able to extract them all, and I maybe don't know what types of functional forms I have within my data. I also want the end result to be interpretable. It has to be something that I, as a physicist, can actually do something with. I need to be able to turn it into actionable information. So I kind of started with the basic approaches, as I think everyone should. So I tried principal component analysis, and I can see some features that are interesting. The problem is that with principal component analysis, you're kind of slowly decreasing the amount of information that you're containing in each component. So every component is not weighted equal. These vectors really don't make a lot of sense. I can't interpret them intuitively. And also, PCA thinks about each individual time step, or in this case, voltage step, which I know happens in a sequence, as completely uncorrelated dimensions. So it's not really capturing the physics or about the actual experiment that I conducted. You can also go and try to cluster into different groups, and you can see some features, again, that have some interesting characteristics. You can see some different shapes, so clustering can give you something, but that still gives you groups of different types. It says I'm either class A, class B, class C. That doesn't tell you how things are varying spatially, which is really what is important for me as a material scientist to do something with it. So I thought, is there a way that I could kind of solve my problems using deep learning and neural network approach? So what I thought about is, how can I make a neural network learn features about this data? So I can start, I have a bunch of ferroelectric hysteresis loops, and I can train an autoencoder. So we've talked a lot about autoencoders here. So I can start with my input and start to extract the most important statistical characteristics about my data set. Then I can compress this information into a low-dimensional latent space and use that through a decoder to start to train it to generate my original curves, and use the information that I have here, which is compressed and low-dimensional, to actually explore and visualize what my space is. So kind of to go a little more into detail, because I have time series and the data, the order of the data and how I collected it matters, it's important to include that concept in the network architecture. So this can be done using the concept of recurrence, where you go through and you take each time step individually, pass it through recurrently, passing information from the previous time step onto the next. And you can have a series of different neurons within that network structure, pass that information on to a series of different layers, forming a deep neural network. And then you can take just the last time step, which contains information about all the previous time steps, and use that to form your low-dimensional layer that actually is where you're extracting some insight about your information. So I show here that I used a ReLU. That'll come into play later in why, and you'll see why I did that. So once you have this low-dimensional latent space where essentially you're having 16 parameters in this case that define your whole entire data set about the different types of spectra that you might see, you can repeat that through time and then pass this on to the decoder. So the decoder can then try to regenerate the original spectra that you saw. And then by optimizing this, or well, actually having at the end a linear output where you kind of have, where you go through each time step, you can regenerate the original time series and then optimize it using kind of standard approaches, backpropagation through time, and optimizing it based on the mean squared error. So in addition, yeah.
So that is, you're just doing an autoencoder, you're not doing a variational.
I have done variational. In this case, I did not do variational autoencoder. It would have been better to have done variational autoencoder. But yeah.
The previous slide, are the layers there the number of time steps? Is it only unrolled 3 times, or is that depth? Which one is the time limit? Oh,
no, it enrolls through the entire time, which is about 96 points in this case. But we have 96 time steps per spectral curve.
So you have this 192 layer step because you unroll it 96 times for each time step, encoding and the 96 decoding.
Yes. Yes. So in addition, because we want there to be information about the short and long-term dependencies within the data, what we do is we use kind of the concept of long short-term memory. So this was what was used in natural language processing a lot, where you have a cell that controls how much information from the previous time step you forget. You have another neuron that learns how much or forms a new memory state that then gets passed on to the next recurrent cell. And then also you have the output from the previous state. So this allows you to pass information through time and give you a sense of both the long and short-term information contained within the spectra that you have. So what happens when I train this network is I can train the network, and then because I never gave it the pixel positions, they're completely uncorrelated. So one way I can validate that I'm actually learning something is to reconstruct the image from the low-dimensional latent space and see if it matches my initial structure. So this is the initial and final image of the region that I was looking at. So this is the low-dimensional space of what the autoencoder saw. But the problem with trying to interpret this is that all these different components are competing with one another. It's very hard to isolate what are the most important characteristics. So but if I were to look at this one example, latent variable, I can see that this looks kind of nice. I can see that there's some boundary over here, and there's a gradient, and there's one type of response, and the rest is 0. So that's what I would want, and that's the concept of sparsity. So I can go and change how I train the network to enforce sparsity. So by adding L1 normalization to that low-dimensional layer, if you have your true value and you propagate out the mean squared error, and here's the error associated with the weights, with the magnitude of the weights from the L1 normalization, you can see that it tries to put values where there's some values that are non-zero, but most of the values are 0. And that's exactly what I want. I want to impose sparsity on this low-dimensional layer. So if I do that and I train the neural network, I get...
Sorry, Josh,
yeah.
You're enforcing sparsity on which weights?
On the weights of the low-dimensional layer, of the low-dimensional layer in the autoencoder.
It's going from your last LSTM to your low-dimensional layer?
From the last time step of the encoder to the low-dimensional layer.
But that just means it's sparse in whatever crazy representation comes out.
It's sparse in the low-dimensional layer.
The activations aren't necessarily sparse, just the weights.
But if you drive the weights to 0, it should impose sparsity on that layer.
Not in the activations, which is what you're showing there, right? You're showing activations, not weights.
Yeah, this is the activation. Yeah, not the weights.
Right, but your sparsity is on the weights, not the activations.
Yes.
Okay.
I see what you're saying. We'll talk later.
Okay.
Yeah. Okay. So what we get is we get these sparse images where most of the responses are 0, and then you have different regions that have certain responses of different magnitudes. And you can think of these as showing I have a character like this, and then I have this magnitude, and I'm turning it up and down, and I can see how I change the different responses. So one thing I think is kind of nice is you can visualize how this, oh, I don't know why that didn't play. You can visualize the learning process. So this is the low-dimensional layer as it's training. So I'm just exporting and then reconstructing the image. And so you can see it starts to kind of learn kind of the same different features. And then as the network trains more and more, you'll start to see certain features kind of coalesce into one individual parameter. And then you'll see it kind of sharpen to give you the image. So you can actually use this as a way to visualize how the training process is going. So these, I think it's cool. Kind of cool visualization.
Looks like many of the units are not being used yet.
Yeah, that's because of the L1 regularization trying to drive the weights to 0, and then the outputs go to 0. So once we have this network trained, we can go and we can modify how we use this network to understand our data. So we have this low-dimensional latent space, and we can then use this autoencoder as a generator. It might have been better to use a variational autoencoder, but we can still generate responses. And for the material science community, and in this kind of in piezo response force microscopy, this sort of approach has not been done before. So once we do that, we can go look at one of these maps and see what happens as we start to take the average values within that map and start to tweak and turn up these different activations. So we can see this is a region that is primarily like a C domain, so we should expect a square hysteresis loop, and that's exactly what we see. So as we're turning up that value, the colors in this hysteresis loop match the colors in this figure, so these correlate, and you can see that you're getting kind of the expected response. So this is giving us some insight about how this response is varying spatially and how that corresponds to the hysteresis loop. So we're able to use that. So this is another example that was more complex and actually interesting, where we can see that we have this boundary, which happens to be the peak side of the boundary. And as we move from this boundary to that boundary, so these are two different boundaries, we can see that we have a different character in the hysteresis loop. And we form this intermediate concavity, which is something we didn't recognize and didn't really know. We saw a few examples like this, but we didn't know how to spatially correlate them to the different responses, and we couldn't see this gradient very easily. So once we discovered that feature, we then, okay, what's the physics? What did that tell us? And we can look at this sort of response. So this is looking now at a different parameter. So every time we saw this intermediate concavity, we saw that there was this shape to the resonance response. So this is, you can think of as the elastic modulus changing. So classically in a ferroelectric hysteresis loop, the elastic modulus, as you switch it, should soften and then harden. So it's like becoming really pliable as the material kind of is unstable, and then as you switch it and drive it into its preferred state and try to reinforce that, it becomes much stiffer. It's like a spring, and then it keeps going and it has like a butterfly-like shape. But in the areas where we saw this intermediate concavity in the hysteresis loop, we saw a very opposite trend. So what we actually saw was the material starts in the uphold state, we apply positive bias, and the material actually hardens. So that's the opposite of this case. And what that is associated with is that material going from the uphold state to the in-plane pulled state. And if you look at the elastic modulus tensor, you see that the material is actually stiffer in the 1,3 direction than the 1,1 direction. And this process happens in reverse. So this is a new mechanism, switching mechanism, that we didn't know existed in this material. a three-state, two-step ferroelastic switching mechanism. And it's associated with a large electromechanical responses and some interesting properties. So that we were able to use this approach for that. But then we went on to say, like, can we actually extract that from the extract more information from the resonance response from this measurement. So this is, again, is the activations trained from the neural network from the resonance response, which had a much more complicated character. The ferroelectric hysteresis loops, we probably could have designed an empirical function or convex hull or some sort of approach to understand them. But the different types of mechanisms of response that we're seeing in the resonance response are much harder to know what they are ahead of time and also to model with an empirical function. So we trained this autoencoder and we saw a lot of interesting features. So you can see there's this gradient along this boundary, and that's associated with a hardening. So the material's hardening as you approach that boundary. So once we figured that out, we thought, okay, what does that mean from a physics standpoint? So we kind of drew little sketches of what the domain structure looks like, knowing what the geometry should be. And if we apply this positive bias right here, what happens is to switch this material, you have to form a charged domain wall between this in-plane polarized A1, A2 band and this newly downward pulled CA domain structure. So that's creating electrostatic repulsion between the two different domains, and that's causing the material to feel like it's harder. So that's actually what we're observing here when we're seeing that. There were other sort of responses. So at the beginning, it starts off being a little crazy, but as we're approaching this boundary over here, we see this double well hardening step just like we saw before. So we're able to capture that in this response. And then again, we can go and we can do these little schematic drawings and see what's going on. So when we apply positive bias switching to the downpoled state, we have to form this charged domain wall. So we're capturing the effect of having to form a charged domain wall here, where you have this head-to-head poled domain. And on the negative bias side, we have to form a charged domain wall as this domain has to encroach on this A1, A2 band. So this is telling us about the switching mechanism where I actually observe formation of charged domain walls, which is important for local conductivity. So knowing that this existed, we can go and have our collaborators use phase field simulations by taking a simulated tip and applying a bias and actually look at the different energies associated with this. And we can actually end up seeing the electrostatic energy emerging just as we would expect right around where that charged domain wall is. So because we were able to discover this in the piezoresponse images using the neural network to help sift through that data, filter out what was important, we then could go to our collaborators and say, do this one experiment. And they did the one experiment, and we were able to understand the physics. So this is kind of another example where we actually see the opposite gradient going on. And what you'll see is you'll see that double well potential form in intermediate steps, and then it just forms a hardening step on one side of that well. So you can see kind of right there now it's switching back. So this is kind of another example where you're seeing as you're increasing that activation, you're having just that hardening step on one side, so hardening, and then it's doing kind of the classical behavior on the other side. And if we do the drawing, we can again see that this makes sense. So if you under positive bias, the material hardens because you're forming a charged domain wall. So again, the polarization directions pointing head to head, so that's causing charge to accumulate there, and that's creating electrostatic repulsion that's making the materials become stiffer. Under negative bias, because of the geometry, this doesn't actually have to form a charged domain wall. This can remain completely uncharged. And that's why you don't see that hardening step, and you see the flat response on the hysteresis curve only on the negative bias side. And again, we can go in and with our collaborators, we can confirm this. So here's the electrostatic energy, so you can see that's the formation of the charged domain wall there. And then if we apply the negative bias where we don't expect to see a charged domain wall, you can see that there's no increase in the electrostatic energy at that boundary. So we were able to use this technique to understand the switching mechanisms. We could go on a little further, and then now that we know that this effect, or this is related to that ferroelastic switching character, we can go in and we can use a convex hull, fit the areas, and create these maps that show the relative ferroelastic character. So how much elastic nature is in the switching process. We can see that this corresponds to that same gradient that we saw from the right-hand boundary to the left-hand boundary, or the valley to the peak. And if we go and we look at when that material is switching ferroelastically, we can look at a different dimension, which is the quality factor. So again, that's the amount of energy the material is absorbing. And what you can see is during that transition, the cantilever actually is not resonating, which means that the material is absorbing all of the input energy. So this is identifying that this particular boundary is particularly good for electromechanical energy conversion. So if you wanted to start to think about how you could design this material, you could go back and try to engineer a larger volume of this material to exhibit this ferroelastic switching behavior based on this geometry. So then we can kind of use simple models and say, okay, we want this geometry to maximize the volume of this ferroelastic switching character without encroaching on these other domains. So we're going back into the lab now and using our rudimentary tools to design these materials to create this particular domain geometry and enhance local electromechanical energy conversion in this system. So to conclude on this section, I talked about how I could kind of engineer new complex domain structures and how I can use recurrent neural networks to extract information and simplify how I identify important features within really large data sets. And this can be useful to understand, in this case, ferroelectric switching mechanisms, but it can also be applied to other techniques in material science. It can really help people, instead of just what's normally done in a lot of the experimental fields, is people choose a few points along an image and they say this is about what it looks like, and then they make their conclusions. They're not doing any sort of statistical analysis on their data. So this is an example data set that I was working my friend and colleague Dennis Meyer and Tor Gren at NTNU in Trondheim. They sent one of their students to work with me for a little while, and they work a lot on europium manganate, which has a very interesting conductive domain wall property. So depending on this topology, how the shape of this domain wall is, you can get very different conduction mechanisms in europium manganate, and that can they're trying to use this to create different sorts of logic in these multiferroic sort of devices. So they did a lot of local IV measurements. So they took hyperspectral images where they measured the current voltage response, so how much conductivity the material has. And then we trained this autoencoder again, and we could clearly see all these interesting features that were relating to the shape and topology of the structure. So this was data that they already kind of analyzed using the manual approach, but with a few days and my student, they were able to automatically extract this. So instead of taking months to discover the feature of interest, it took only a few days. So these are just kind of the example generated curves. These curves are much more simple than the curves that I looked at with my piezoresponse force microscopy, but again, it was able to identify the important features that they could then use to analyze their material and understand the physics. I also took this approach and looked at this technique called electron energy loss spectroscopy. So this is an electron microscopy technique where you take an electron beam and you have a very, very thin material that's electron transparent. And you can have a series of different detectors, but one of the detectors is called electron energy loss spectroscopy. So what this is doing is it's measuring how much energy each electron is losing as it's interacting with the material. And that can tell you different things about the coordination environment and the electronic bonding state of the different atoms within the system. So this is some work I did with Mitra Tahari at Drexel, but she's now moving to Johns Hopkins. And this was a paper that they published in 2015 where this is a heterostructure of LSMO and lead zirconium titanate. So these are two different materials, and they were looking at what the effect on the charge state at the interface was. And as kind of common in this field, they collected hyperspectral imaging. So they have a spectra at every single pixel position. But because it's really hard to analyze and the curves are noisy, what they did is instead they just took a few points as they moved from the bottom to the top across that interface and tried to understand the relative trends that they saw. So I said, oh, can we do better using my approach? So I took I took the data set that they had, went through and trained the recurrent neural network again, and I can see this is just at the boundary between so this is the LSMO and that's the PZT, and I can see that I can capture where the atom positions are just from the spectrum and the low dimensional representation. But what's really interesting is this image right here, because this is showing the kind of how much diffusion or how much variance there is at the interface, and that tells you how far the electronic properties are changing at the interface, which is something that's very hard to extract using other sort of approaches. So we can then go in again using the neural network as a generator and trying to see what the different embeddings or low dimensional representations are encoding. So we can go through and we can see at this interface right here that you're having mixing of the lanthanum and manganese at that interface, and it shows how sharp that interface is. So this provides kind of a qualitative measure of how good your interface is, which is really important for a lot of different properties designing 2D electron gases where you have locally conductive materials at interfaces. You can also see that there's changes in the peak structure right here at of the oxygen, so it's changing its screening length. So you're seeing changes in the oxygen coordination. You can also look at, and this is at the LSMO layer, so there shouldn't be any titanium, but you can see some emergence of a peak that's associated with titanium. So that can provide insight into how much intermixing or how much titanium you're having diffusing at that interface, and can give you a sense of the quality of the interface. So this then could help us address how can we design our synthesis routes to really improve the quality of the interface where you're getting functional properties. And again, because of this changing structure, you can also see interesting changes in the oxygen coordination. So now we're going back, and again, we're going to go rely on DFT simulations to try to understand what's the changing electronic structure environment that this autoencoder is detecting at that interface. So I like to think about a little bit of what's next for experimental science. So I saw I like all the talks that we were seeing on robotic synthesis, but I think that as an experimentalist, there are a lot of things that are just really difficult to automate in terms of synthesis. So we can't just rely on that approach. That's a good approach, but I think we need to think about how we can make our job as experimentalists easier. So if I were to think about how the experimental world has kind of devoted their effort, I would say it kind of looks like this, where a lot of people have spent time focusing on algorithms. There's been some work on kind of managing scientific data, but as that happened, the experimentalists kind of move out of the way and aren't as involved. And then if you think about hardware infrastructure for experimentalists, it's really underdeveloped. And we really need to flip this around. And the question then becomes, how do we fund it? So I think we really need to focus on how we can try to fund really much better ways to collect scientific data and much better hardware infrastructure that enables us to conduct data-driven science. Because as experimentalists, we're throwing out 99.9 going on for a long time % of our data. So I've started to work on this. So I started to think about what our current workflow is as experimentalists and how we might be able to address that. So we generally start out, and this is kind of for synthesis, we start out with conducting synthesis and doing characterization. And generally, all of the software and all the instruments we use wonderful proprietary file formats and software. And what is most common is that students go in and they convert it to standard formats like CSV and TXT. What happens is we throw away all of the important metadata. So that's one area that we really need to improve is trying to save this metadata and information about the experimental process. Typically, students will take notes, handwritten notes, which never matriculate into the world and are never, most of the time the student can't even find their notes from a long time ago. And then there's some human interpreter who goes through and picks through different dimensions in space, tries to understand it, and creates visualizations, most likely on Excel, because that's what students like to use in material science. And then they might put it on a local computer with some wonderful file name with a long string of things and then good and various numbers. Then we do a great service of publishing that data, and then we put it behind nice paywalls, which generally exist, and then we never actually share the data. So we really need to think about how we can redesign our approach. So I'm working on developing and really focusing on the human aspects of how we collect notes. So how do we create a user interface that is really seamless and user-friendly so that our students want to take notes in good ways and want to store that data? How do you create real-time visualizations of the information so they can actually make realistic and actionable decisions based on their data instead of just collecting a bunch of data, spending a month analyzing it and coming back and doing an experiment after everything has changed? How do you kind of take these proprietary formats and place them in a standard format so we can develop packages for analysis so that we don't have to reinvent the wheel every single time we want to make the same type of graph? How do we create a pipeline where we can immediately provide some basic insight using machine learning so that we can at least have some sense and help make our decisions faster without having to go back to the wheel? And then how can we store this data in a way that is findable and accessible? And then with the ultimate goal of then being able to have communal analysis. So once the data is available, we can all go in and do various different approaches and see how we can extract different insight from that data. So this work is largely associated with this nano-human interface initiative that was funded out of Lehigh. So this is kind of a little example of one thing we're trying to do, where we're trying to understand the human element of using electron microscopy. What are the challenges that a human faces when they're using the instrument, and how can we simplify their process so that they can interact with their materials better, understand what's going on, and make better decisions during that process. So this involves kind of hooking people up to the cyborg system where they have EEG monitoring, eye tracking to understand what's going on, be able to track decision making and be able to have rewind buttons on the electron microscope. As part of this, one of the really important areas is focusing on how can you do real-time machine learning. So how do you do high-speed machine learning where you have real-time analysis? So you can't rely on sending data to a cloud. You can't rely on even sending data to a CPU if you're doing to CPU and GPU. You have to use specialty hardware. So how do you deploy models on FPGAs and make them run in real time to provide feedback? So this is just a little example of some work. So this is work with Kate Arrington, who's a cognitive psychologist, focusing on the kind of tasks that a user does with the electron microscope. And this is a low-hanging fruit because the electron microscope is a total mess in terms of how the interface was designed. No one devoted any effort to actually trying to design this in a user-friendly and meaningful way. So you can see how much your eye is jumping back and forth, and each of those individual steps is a distraction that's preventing you as a user from making informed decisions. And the biggest problem is that there's no ability to conduct analysis on the fly. So even providing basic analysis on the fly will really help our ability to conduct science. So one of my roles in this project is thinking about how I can use high-speed machine learning. So I've started by just working with actually deploying that recurrent neural network model on Azure Cloud using FPGAs. And you can really, really reduce the latency time. So on a GPU, CPU sort of process, you have about 50 millisecond latency, where you can get it down to 3 milliseconds. And this matters if you wanted to actually do some real-time analysis and real-time control. And one of the biggest problems that you have to focus on when you're deploying on FPGAs, you can't deploy as large models. So you need to think about how can I trim my model. So a lot of what I'm doing is focusing on how much can I prune out different components of my model and still have it give me good enough performance that I can actually extract some insight, but also that it's small enough that I can fit it on the current architectures of FPGAs. So this kind of leads into the next kind of area where we're really kind of increasing the speed of our various characterization techniques. So this is work again with Mitra Tahari, and she does a lot of EELS, spectroscopy. So that's the electron energy loss spectroscopy. But she does a lot of, she increased the speed of the detector such that she can do in situ measurements. So she can oxidize materials within the electron microscope. She can change the temperature and measure EELS spectra, so hyperspectral images through temperature time or through oxidation time and see how materials are changing as they're reacting or changing their temperature. So this is a kind of recent example where they can collect data at 26 gigabytes per second. So this is EELS spectra, and it's at 400 frames per second of EELS data, so hyperspectral images at 400 frames per second. So if you want to be able to interpret that and use that in a meaningful way, you're going to really have to rely on these high-speed machine learning approaches and new algorithms that can help analyze this information. So with that, I'd like to mention that we're kind of, as part of this, running a little conference and one of the main aspects of this for the electron microscopy community is bringing in more data analytics and AI into our community. So if you're interested in kind of sharing your experience and think it might be applicable, I'd invite you to email me, and we can talk about how you can how you could come and give a talk at this conference and interact with this community, because they're dealing with a lot of data problems, and as a community they're struggling to figure out how to really make the most out of all the expensive effort and a large amount of money they've invested in their equipment. So with that, I'd be happy to take any questions. The code for the autoencoder is all published on my GitHub. This is a link to the GitHub repository. And with the paper, I included a Jupyter paper, so it's a full paper, as well as all the code associated with this work in a Jupyter notebook that can run on Collaboratory, or you can run it locally on your own computer. So with that, I'd be happy to take any questions.